It's going to be a similar format to what you guys had before, and that there's going to be around 34 multiple choice, and then there's about 15 points worth of the short answer. All right, and I'll give you some details as to what some of the short answer might be. If you're here on Monday, you're already going to know one of those particular hints, but I'll recap that. All right, so any questions about our exam coming up in terms of different clarification? Let's get started. So I have your clickers out with a few kind of clicker questions along the way. And then this little kitty here we've got is our cheetah. And I think of this creature particularly when we think of athletes and one of the ultimate athletes when it comes to speed as a mammal. And so one of the things we'll take a moment to think about is what's special about this creature in terms of its athletic heart. And if we think about athletic hearts, and then also just everyday kind of hearts, and then also hearts that might actually be pathogenic. What is different about those structures? Some of the things we'll be looking at today will approach that topic. All right, so again, hopefully you guys know exam Friday. So make sure you're covering that, and that's covering from endocrine on through the heart. And then what we'll do on Monday is start to tackle aspects of blood and vessels and get into the immune system and so on. Again, homework number 2 will be due on Monday after the exam. So make sure you've been looking through that. And again, we'll wrap up the heart and do a little bit of review along the way. There's a video that I'm going to start out with today that actually involves research that's done at the U. And I'm going to be kind of annoying during it, and I'm going to ask you guys questions about the heart as we go through as part of a review aspect of it. So think of this review, this video as a little bit of review of some of the things that was covered with what Tyler went over. So we'll start out with that, and then get into some other aspects.
The University of Minnesota has been at the forefront of mending broken hearts for the past 50 years. Hidden away in its basement, scientists have found a rather unusual way of looking at the heart, and in doing so have come up with improved ways of fixing it. Hi Paul, I'm Kevin.
Nice to meet you. Come on in. Yeah.
Paul Yasso is a professor of surgery at the Visible Heart Lab. He's perfected a technique for bringing dead hearts back to life, giving scientists a unique opportunity to study the heart in motion.
What we're going to do now is we're going to cardioplete this heart, remove it, just like they would for a heart transplantation. But instead of planting it in another animal, we're going to put it on the visible heart apparatus.
Paul's been developing this technique for donated human hearts that aren't suitable for transplant. But for today's work, they'll use the animal heart that most resembles ours in size, structure and function, that of a pig.
And now you can see how flaccid it is.
The heart is taken off to be prepared, and an hour after it stopped beating, Paul is ready to reanimate it. And you're about to take this heart, which you stopped with a solution some time ago now, and you're going to make it beat again.
That's the hope here.
And that helps you because
now we can really study functional cardiac anatomy.
if they can get this heart beating again, it will give them remarkable insight into its function.
Now we're flushing the cardiac leach, it's warming up, and you can actually see some spontaneous contractions occurring.
The generally fibrillating heart.
Alright, so real quick, neurogenic or myogenic?
Myogenic.
Right, and then this thing is outside the body, adding particular solution, ions and so on, to get that little funny channel of the SA node to go and spontaneously start beating again. Again, this is reanimation of a heart, so that is a unique aspect in terms of myogenic. Just to back up just a little here, as we're staring at this lovely structure, all of this here, so this chunk, that's all ventricle. So that's left and right ventricle. This cute little ear flappy thing there, and then there's another one on the other side, are the auricles of the heart. Those house the atria. So as we think about the powerhouse of the heart, where all the pressure is, where all the musculature really is condensed, it's all about here, okay? These are just kind of temporary storage aspects of it. So continue to watch this reanimation of it.
Oh, that's good. To bring it back to life, Paul gives it an electric shock.
And all the shock it's doing, it's already beating, it's just getting
So
it
one
to be more
shock did it.
rhythmic,
Now we've got
rhythmic.
pressure developed here by this heart. So you can see the ventricular pressures are back, right ventricular pressures are back. And so basically it's a little arrhythmic now, but in a few minutes we'll get back to more normal rhythm.
Well, that's fascinating. I suppose it's really quite amazing to see a heart reanimate like that, I think. Now that the heart is beating again, I'm going to be able to look at it in a way that wouldn't otherwise be possible.
And if we actually dim the lights in the room, I'll be able to kind of give you a tour of this functional anatomy.
Oh, that's amazing. Using a tiny fibre optic camera, they can get right inside the heart and examine every aspect of its internal structure. I'm watching this, Paul, and I'm reminded of that film. I don't know if you ever watched it, Fantastic Voyage, where those guys shrink themselves down and go flying through the body in this vehicle. And it's bizarre, because, this is the real voyage. You're really going in there, you're really in there with cameras, you're really seeing this stuff.
I agree that it is like a fantastic voyage every time, and it's a different voyage in every heart. Every heart's anatomy is different. We look at this functional anatomy, how delicate but yet complex.
Gosh, you could watch that forever. That's just amazing.
All right, so just a pause here. As they're looking at this aspect here, and you see all of those kind of webby components there. Those are connected to, of course, some AV valves. So the heartstrings of your heart, what do you guys remember those are called? Chordae tendineae. Good. And then you may have seen just kind of those quick flaps that were there. Those were in connection to that, so those may have been the tricuspid, bicuspids that are there. And then also where we're seeing some other flaps going, where there wasn't that association with the chordae tendineae, those would have been your semi-lunar valves. Okay? So just coming back to some of those aspects of the anatomy, but the functional anatomy of the heart. So I'll post that later, so you guys can go back and look at that. It's kind of neat, and it just brings back so many concepts of aspects that we've been discussing, but it's also something still I'm in awe over watching a beating heart like that. So, any questions before we move on from there? So, a quick kind of review of our anatomy, but actually seeing it in action as it's working. Well, coming back to some stuff that we've talked about before. So as we're looking at here, we discussed the way in which the heart beats. We get that it beats, we feel it beat when our heart's racing. But coming back to the conduction system that's there. So again, starting it out, that's our pacemaker, that's setting everything in motion, is our SA node. And that's going to be a big player in terms of getting the pace started. It's something that, as we think about, we'll have this interesting depolarization that works its way across the atria. And then we'll be signaling to the AV valve, the atrioventricular valve, and then that communication continues on in this bundle of his, down the bundle branches into the Purkinje fibers to help with the depolarization that's going to work its way down the ventricles to allow for those two to contract. All right, so make sure you know that flow of the conduction system. And I just have a quick multiple choice here for you guys. I'll open it up. And you can actually talk to somebody next to you just to make sure you think you've got the right answer here. But this is coming back to that aspect of watching that video and some of the things we've talked about. So I'll give you guys a couple seconds or so to work this out. Click in when you think you've got it, but feel free to talk to somebody else next to you. But what do you think? So polling's open, and feel free to discuss.
It's not a... I almost want to think it's none of the above.
Me too. I'm thinking
It's like I thought it was pretty much spontaneous.
it is. It's all by itself.
That's the AV. No, that's where it all starts. So. Doesn't need stimulation.
I didn't think so, at least. You might need stimulation if it stops, but...
Maybe the AV, it wouldn't be the AV node alone.
No, the AV node is the one that's in the middle here. That's triggered by the SA.
Ah, okay. Cool. It's got to be even.
Although I think the guys lecturing say that sometimes if the SA node stops working, the AV node can sort of take over a little bit.
Yeah, so it still wouldn't be that.
Doesn't sound like
Yeah, still. None of these make any sense to me besides none of the above.
Why is it? Oh shit! Did I change it to AA?
I have another class.
Yeah, it's right before this
Go
one.
ahead and close the poll.
Good thing I just barely got it
John,
in.
you got it, but we'll go for
This is for points. She said, remember last time? She said on Wednesday we're going to do.
And at least
Quicker
50%
points.
of you guys are getting it right. So as we look at this, action potentials in the sinoatrial or SA node of the heart would not occur without. So as we think about this aspect, something should seem a little fishy about this question already. The answer is actually E, right? None of the above. Right? So as you think about this, why would that be? Well, again, you guys all said that was a myogenic heart. All right? In that, there's a spontaneous, it's weird, I know, spontaneous nature of the heart. The SA node can be, whether there's endocrine or nervous connection, it's independent. All right? That's a weird thing compared to, let's say, an insect heart that is neurogenic. All right? So that is independent of this. So stimulation via the sympathetic system, yeah, that it influences the SA node. A sympathetic is your fight or flight to speed it up, but I could sever that part of that nerve, and your heart would still beat. The SA node would still go. All right? Same thing, you should kind of sense something fishy, especially when A and B are kind of like, whoa, similar in that. We know that the endocrine is very much tied to the sympathetic. Epinephrine, norepinephrine, your adrenal medulla. All right, whoa, there's something, I don't see all the above. There's something kind of fishy going on here. All right, so as we think about these components, don't forget, we got a really funky heart. It's myogenic, that SA node, it will beat. Only influences it has is speeding it up or slowing it down via the nervous system or your endocrine system. So, okay. All right, so let's come back to some of these concepts that we were talking about last time. And that we were looking at this graphic that Tyler had gone over, and I wanted to just kind of bring back some aspects here of just coming back to the sense that if we know how skeletal muscle works, we know that's an voluntary aspect of our contractions. We know that there's a nervous system component that's there, and that's an electrical aspect of our motor neurons. And then, of course, we know that there's then what goes on with the muscle. And so this top graphic here is illustrating that aspect. And a really interesting component of what we call the latent period, of there we've got all the nervous system kind of communication, and then it's like delay of all those cross bridges forming, and now we've got our muscle contraction and so on. As we compare that with our cardiac muscle, we notice that the whole action potential thing that we've stared at before in neurons looks really different. When we look at, let's say, the action potential going on within a cardiac muscle cell, where there's this really weird plateau that occurs. And then we can also see that there's an aspect of our muscle contraction that's very much overlaid with that. All right? And as probably Tyler brought up, there's an interesting aspect to this of the fact that we are now talking about not just sodium involved, but there's going to be calcium ions that allow for that plateau. And as we start to look at this, well, why? I mean, well, why does that look so different that's there? Well, notice this refractory period. It's quite extended with that plateau. This is one of the means by which we look at in terms of no matter how frequent or powerful a stimulus that's going to be here, it kind of gets ignored. This is where we have a nice prevention of fatigue of the heart. All right, we know that these muscles, if you work out or do anything, these stairs are crappy for me now that I have this extra weight. You get tired, right? Your muscles do that. But your heart, you better not get tired, right? This is a thing that's working pretty darn hard, contracting a lot. All right, so this is one of these ways in which we prevent what we call tetanus. All right, with this extended plateau, preventing fatigue of the heart. All right, so this particular diagram is bringing this all up again about some of the details that are going on in terms of the action potentials that are occurring. So there's the memory potential, there's time, and in the green it's representing pretty much aspects of, let's say, the SA node in this particular example. And then looking at the actual muscle itself and what's going on with its contraction that's there. So again, just start to come back to the idea that calcium now is actually a player in the action potential. When we talked about aspects of our nervous system in general and components involved with that, it was usually just about sodium. Here we're saying, okay, sodium and calcium are involved. Calcium was keeping that plateau. So this slide here too just further emphasizes that component of what we expect to see when we compare cardiac versus skeletal muscle, right? We don't want the cardiac muscle to fatigue, right? So we have the sustained aspect of that plateau that's there, and again, interesting correspondence with that, with the muscle contraction itself in terms of time, and again, what are we trying to prevent? Tetanus. So as you think about it, your skeletal muscle's got all kinds of graded movements. You can hold something very gingerly, you can hold something very tautly, and that involves aspects of frequency that's there and intensity that's there that is part of tetanus. Here, this is kind of avoided in this sense, and again, to prevent fatigue. So, this is important. Intent, not. Make sure we've got that. As we look at this set of images here that have the memory potential and the time, you're noticing that we can measure all this electrical activity from not only the SA node, we can check out what's going on in the muscle of the atrium, to the AV node, and so on. We're going to start to look at what that all means in a bigger scope of things with this next image. And this is something you probably are familiar with if you've checked out medical aspects, maybe even had such a thing done like an EKG or an ECG. And this is illustrating all of those electrical communication that goes on from the SA node and on. That's what a EKG is. All right? So sometimes I've had students look at it and be like, well, isn't that just an action potential? It's many action potentials all summarized. All right? It's not just one. It's a whole summary of all of it. And it tells you an interesting story. So as we look at this top part and kind of how the graphic goes, is that you're going to be having a first little wave that shows up. That is your P wave. I love markers. So as we see this, we've got our first wave, the P wave that occurs. And you can kind of start to see what's associated with that. That is communicating all the kind of electrical information that's going on with the SA node and also aspects of the atria. Okay, so as we look at that, you'll notice the wave, the depolarization that's working its way through the atria. That's all summarized in the P wave. As we start to look at this next set, so as we communicate from the AV node on down through there, there's going to be a lot of chemical or electrical communication that's going on. Consider all the nodal system that's involved with that. And then also, this is a huge piece of muscle that's there that's getting a lot of electrical activity. So this next spike in your graphic is huge. All right, that's a big summary of a lot of information that's there. We call that your QRS wave that's there. Big spike, because it's summarizing AV, bundle of His, bundle branches, Purkinje, and then all of this myocardial action potential that's there. So a pretty big wave that's present. As we think about this aspect here, where you see the green, again, there's electric activity when we think about even repolarization that occurs too. And so we do get a nice little blip as well with the repolarization and it's going to be our T wave that occurs. We can think about that there's repolarization that occurs with, of course, the atria as well, but pretty much that's a little bit more overshadowed by all the electrical activity that's going on within the ventricles at that period of time. It's an interesting aspect of just all that summary of information that's there. So this graphic's kind of nice in that it does just show you step by step all the different waves that are included in discussing the electrical activity of the heart. So, as we continue through, just this image is actually quite nice. And I like that it kind of just shows the rainbow aspect, but also all the different aspects of the electrical communication and how those connect back to your P wave or your QRS or the T. Right? So be careful with this, make sure you understand what really is an EKG or an ECG. All right, so questions on this? All right. So in addition to thinking about, okay, now we can measure and understand the electrical activity of our heart, we can look at these kinds of things. The other aspect is that you probably have heard your heart, all right? You may have gotten a chance to use, let's say, a stethoscope, or again, you've just kind of sat really quietly and you can feel it beat, or maybe even hear it beat. So as we think about that, there's these heart sounds that are associated with it. And so as we think about this, the closing of the particular valves that you saw in that last video, and then kind of the push of blood against some of those walls can create a sound. And so we call these the S1 or the S2 sound. Sometimes we see it here, a third sound that's there, especially with young hearts, as the blood's kind of swishing around. So when we think about that, you probably heard the love dub aspect of your heart. And so just real quick, we can listen to that. Just to hear the rhythmic component of it. So, again, I love that. Soothing as we listen to it. So as we think about that, that's coming back to some of the functional anatomy that we were hearing. So when we associate your S1, that's about basically, you can kind of think of the closure of your AV valve. So that means your mitral valve, your bicuspid, or your tricuspid at that point. And as we think about the S2, that's the closing and kind of pushing up against the blood there of the semilunar. So remember, there's the aortic, semilunar, and then we've also got the pulmonary aorta or atria that are there that are also arteries that are part of the S2 semilunar closure. So you've probably heard of a murmur before, and with that, it's kind of an interesting aspect where we come back to these valves, and remember that the purpose of the valves are to prevent backflow, right? And so if we have a nice clean closure of that, we should be just hearing simply the love dub that's there. But if we start to hear some other kind of aspects of sound there, that may be a murmur, and that we're experiencing a little bit of leakage that's occurring there. That might be due to a narrowing of the valves or a hardening of those flaps that are there. That can provide a little bit of turbulence and some leakage through. So again, there may be an aspect of another sound that we hear. So as we go through, and this will be also some more review as we discuss aspects of our blood flow, to make sure you know your flow of your heart, and that does mean knowing some of the anatomy of it. One of the terms that was used when Tyler was going over this was the term systole or diastole. Make sure you're comfortable with that. When we think about systole, we're going to be talking about the contraction. It's the contraction of the atria, contraction of the ventricles. Either way, it's systole or systole. As we think about diastole, okay, these things are going to have to relax. And so one common thing that is gone through is the cardiac cycle. And this is something actually you guys already know. But what the cardiac cycle is taking a moment and snapshot in time of the heart and just taking a moment and do we understand everything that's going on with that heart at that moment. All right, so we're going to kind of go through a little bit of this and treat it as a review of some of our concepts that we've just been going over. All right. So, this is usually a scary diagram, so that all physiology students scream out when they see it. But this is a diagram that actually shows all the amazing things that you can see in one snapshot of what's going on with your heart. So as you can kind of start to see, there's aspects here of the heart sounds that we just talked about that are located here. Also overlaid with that is the EKG, the electrical nature of the heart that we've just talked about. We can also start to associate aspects of volume with your ventricles, and then also start to understand pressure that occurs within the heart to get that blood to go to its next location, to the lungs, to the body. So all it is just looking at a little snapshot and summarizing what's all going on. So what we're going to do is just kind of take a moment and review an aspect of the heart with a diagram, and then connect what we think is all going on with it, and then we'll come back to the notes to recap that. Alright, so as we look at this, let's say we've got our heart that is here. We've got the 4 chambers, of course, and you probably hopefully all know about your chambers and the flow of blood as we think about this. So one of the things that we can think about is, let's say at this particular point in this heart, we've had our blood flow into all the different atria. Now it's dumping into the ventricles. And we're going to just take a moment and say at this particular period of time, this is where the heart is right now. Okay? So again, assuming you know your flow, all that good stuff, that this is the snapshot in time where we've paused, we're looking at the heart at this moment, and we notice, okay, blood is both in the right ventricle and in the left ventricle. At this point, it's not quite yet going off to the body, not yet going off to the lungs. This is just where it is, and we pause time. So from this drawing, I want you to work with somebody next to you and tell me what would the EKG be at this point. All right, so what would we expect to see in terms of the waves at this snapshot in time? What about the sound? All right, what will we have heard at this point in time? All right, as we think about this, what can you tell me about what the atria have done or are going to do? And same thing with the ventricles. All right, what's coming up? What has it done? What's going on at this particular snapshot in time? So take a second, talk to somebody next to you. But what can you fill in all the blanks as to what's going on with this heart at this second? Okay, so EKG, the sound, what's going on with the atria, what's going on with the
Is
ventricle?
the Q where that's at? Because then the ventricles are going to go, and that's going to be the big wave?
Yeah, it's like right. So I think that's right. So it's right before they compress.
And that's the big one, right?
Yeah,
Or the strong part. So that's got to be, we got to be at the Q part, I guess.
Yeah. It'd also be at the point where the AV valve is snapping shut. So that should be the S1 signal.
Yeah, that's one.
I would think that the atria are.
Or well, that's about the closing of it?
Yeah.
Okay. All right.
So I would think that right now the atria would probably be contracted, but are in the process of relaxing. But the ventricle, the opposite, they're being ready to go.
Okay. Makes sense to me. What's the P wave? What's that P? Yeah.
That's the atria going. It's much smaller.
So they pump into the ventricles,
Yeah.
and the ventricles push it to the rest of the body, and then the T is what, the relaxation? Or no.
Apparently,
The S would be the relaxation.
I guess it sounded like it had something to do with the repolarization or something she was describing. But that seems weird to me to have a pump like that. I don't know.
Yeah.
All right, so let's go back to this real quick. So as we look at this image here, it brings up some aspects that we've been talking about. So as we stare at this moment in time with this, let's first go with this. What did you guys say about the EKG? what would we be seeing in terms of core connection to this snapshot? What wave are we seeing?
Q?
QRS, yeah. So at this point, we're seeing this taking place, and that we're about to get going with a good contraction here, get the blood off the lungs, get the blood off to the body. So the electrical activity should have happened at this point. I mean, we were trying to be snappy here about getting this blood out. So that electrical activity from your AV node on down to the Purkinje fibers will have happened, and we just paused at this point. But that, again, that stimulus, all that there has happened. So yeah, your QRS, something that's taken place. How about a sound? What do we expect for a sound? What have we heard? Yes, one. Yeah, closing of our tricuspid and our bicuspid at this point. All right, so yeah, the S1, yeah, we've heard that. That's happened. We heard the lub. All right. Now, as we think about what's going on with the atria and the ventricle, now the ventricles, they're getting ready to contract. All right, so we know that's a part of this process. And we know that it would be, at least in order to get the blood in here in the first place, these guys had to have contract, and most likely now they are relaxing, right? So going through a period of diastole. Okay? So yeah.
I have a question about the QRS. If the ventricles haven't contracted yet, wouldn't that not be present?
Sure. So for the most part, most of this has continued through. So in order to get ready, because this will be the next step, that communication, that electrical communication will have happened. The pressure is going to start to build, but the actual expelling of the actual blood at this point hasn't.
Oh.
So the electrical aspect, yeah, but the actual contraction of it, not so much yet. Yeah. So we're not all about the electrical activity of it at this point, but not like the muscle tension. So, all right, so good. So that's all that cardiac cycle is. It's just scary when you first look at it, but it is just taking a snapshot in a moment in time and to asking yourself what the heck's going on with the heart at this particular moment. All right. So you guys answered this beautifully. So as we look at this, again, scary drawing, I know. We can look at this point in time that we drew and think about what's going on with the atria. Yeah, we said, okay, it's repolarizing, how you're relaxing at this point. We've got the ventricles doing their QRS thing, starting an aspect of contraction at this point. You guys told me the S1 sound is there, absolutely. And at this point, what we say is that this is isovolumetric, meaning that in this snapshot of time, I can look at the volume here, I know what's going on with it, nothing's moving. This is an isovolumetric time period. The moment this stuff starts flowing other places, I can't clearly keep track of what's going on with it quite yet. I can't say that's isovolumetric, but at this point I can. All right? So these other aspects just continue with that. Well, what happens next? You know what happens next. We've got to inject this stuff. So blood's going to be flowing through the body, and as we think about this, that ejection period, there's the actual contraction of the ventricles that occurs, and then of course we're going to want to see those muscles also repolarize as well, so we should start to see our T wave and so on. This is an interesting aspect. About 70 ml of the blood is going to be ejected, and 60 is left behind. All right, for, let's say, a typical normal heart. Usually these are based on a male. So again, something that we'd be seeing in this case. So as we think about this, there's an interesting aspect of thinking about stuff gets left behind. Oh, okay, that's kind of interesting. So yeah, and again, depending on the health of your heart and how efficient it is, maybe more or less will be left behind. So, as we look at this, and we'll come back to that concept a little bit later, as we think about this other aspect that's there, we may have expected here, let's say the S2 sounds. Again, that's after the blood's been gone through, slamming shut the semilunar valves. Here we hear that part of our heart. And again, now the blood's out into the rest of the body. This is also what we consider isovolumetric at this point. So, again, just aspects of looking at little snapshots along the way. Now, just to come back to that idea that we just discussed about, well, okay, what about what goes on in the heart and what's left behind? And so you may have heard of aspects of cardiac output or stroke volume. to understand the health of your heart. So what I'm going to illustrate next is some of that stuff, just to give ourselves a little bit more perspective of what we can tell when we look at a healthy heart or a heart that maybe isn't so healthy. So as we come back to the heart, and again, our kind of classic drawings here of our 4 chambers. As we just talked about, there's an aspect here of, and I'm just going to focus on this side of the heart, of their blood. Okay, blood that's filled into our left ventricle. And as I mentioned, there's an aspect of a volume that's going to be present in here. So there's 2 different numbers that we can look at. One is going to be this end systolic volume. So again, systole refers to what? Or systole? Contraction, right? All right, and then also we're going to be looking at something that's called the end diastolic volume. So again, what we have at the point of relaxation, right? So at this point, this particular volume that we're looking at here is what we're seeing before it's contracted, okay? So at diastole. So you'll notice, okay, looks pretty good. There's a lot of blood in there. Ooh, all right. Now, let's say I'm going to go ahead and contract, all right? And there's only a certain amount of that blood that's actually going to go through the systemic circuit that's there. I'll make a magical line, let's say here, all right? So this is the stuff that's going to go. This is the stuff that remains. So again, that end systolic volume is the stuff that, illustrate again, all of this would represent the end diastolic volume. But at systole, I said this stuff's going to leave, and then this stuff is what remains. So it is this that is your end systolic volume. So the stuff that's left over. So when we take those 2 numbers and subtract them, this is what we get that's leaving and going to the body, right? That's your stroke volume, so your SV. So, an interesting aspect, right? And that, okay, there's a bunch of blood that dumps in, okay, and now I'm resting. That's your end diastolic volume. And then my heart's going to get ready and ramped up and boom, contract. And then there's going to be stuff left over. So that is your end systolic volume. What's been going through now, the rest of the body, is your stroke volume. Now, the stroke volume, that's kind of helpful in understanding your overall health of your heart. Because you imagine, this is the stuff that's going in your body, right? This is the stuff that's containing nutrients, oxygen, all the good stuff. So you probably want more of that circulating through to do the work that you do. All right? If you have a scenario where, let's say this is just okay, but what if we move this line on down even more? All right, that might be a better and healthier heart, where there's just a minimal amount left over, and a good chunk of this goes into now your systemic circuit. All right? So to understand health of your heart, you take the stroke volume, and you also pay attention to your heart rate, okay? And that's your cardiac output. Putting all those components together, your heart rate times the stroke volume, cardiac output. A good way of understanding your health of your heart. So I want you guys to take a second and talk to somebody next to you. But as you look at this heart and think about the ways in which things can be pumped and more can be pumped out or less may be pumped out, how do we manipulate that? All right, so take a second, and actually I'll take a question.
Yeah, I have a question. Okay, so your cardiac output is like the health of your heart protocol. But you have let's say athletes have lower heart rates, so their number is going to be multiplied by a smaller amount. So it corresponds to theoretical.
So it depends on the athletic hearts that we're looking at. So that's a really good point. In terms of a healthy athletic heart, you usually have a lower heart rate, and then there should be a connection to a better overall stroke volume that's there. So that's what I want you guys to think about for a second, is how do you improve stroke volume? Okay? So one of those ways is influencing a little bit of heart rate that's there. But also, as we think about it, what can we manipulate here? And that's where we think back to the cheetah or other athletes that are there to improve that stroke volume. What do we need to do to improve it? Or even think of the flip side of what would be a diminishing aspect of it. Because we have to consider what kind of athlete are you looking at too. All right, so take a second and think about ways in which you can manipulate the stroke volume to, let's say, improve it. So take a second, how do we do that?
Increase the muscle.
So that's, I think, can pull in tighter, more muscles, so push more volume, more blood out.
Yeah, but they'll also be
Now, when we build muscle, do we build it on the inside of the chambers or on the outside of the heart? Or do we actually decrease the amount of volume?
No, I think it would be the same, but you're just increasing the muscle on the outside.
I mean, that's what would make sense, but it's not necessarily, it doesn't
Although
necessarily
it could grow a little bit.
Yeah.
Just from pumping so much blood How about the endurance? Yeah, I mean, athletes have lower heart rate because they can, one pump is so much stronger, just
Pumps a lot more blood.
yeah, in one beat.
I don't know. Yeah,
Too easy. Too easy.
Yeah.
So let's come back to this real quick. So as we think about how we might improve or understand the difference between a healthy heart and a heart that maybe is not so healthy, what are some of the things that we can maybe associate? If we're going to design and make the best heart ever that is going to have a really nice stroke volume in terms of maybe very little of this stuff hanging out, most of it being ejected out, what were you guys thinking in terms of designing this ideal heart? What were some of the things that came up? Yeah?
Have a stronger heart that can press more to push more stuff out.
Okay, make it the muscle itself better in some way so more just gets pumped out. And that's, again, one of these ways we can start to think about differences in some of the heart tissue. So if we come back to just simply the myocardium that's here, maybe we have some more muscle that's here. So as we think about, and I used that weird example before of like, why does my deltoid look like it does versus someone who's really lifting a lot of weights? We can start to think about some of the things that might be different within the myocardium that's there. Maybe there's more of the myofibrils packed in there that can, help with a stronger contraction that's present. What are some other aspects that if we're going to improve that actual muscle tissue that's there? What has to go with an aspect of contraction?
Heart rate?
Okay, so heart rate. So they're building a better muscle that's there to have improved efficiency of not having to beat as much, it's just stronger. So building those myofibrils, not a bad way. What are the storage tanks, again, that we need in muscle?
Maybe wider veins and arteries.
Okay, so we need to do those connections too of getting it in there in the first place. Actually, that's a really good thought in terms of this being a muscle itself. It needs nutrients. It needs all this stuff. So you can actually start to see differences in the coronaries that are all located within that as well. What else? To have a contraction, we must need what? Calcium, right? The storage tank of calcium or the sarcoplasmic reticulum. Pack that more in there as well. All right? Maybe even more mitochondria. Aspects like that are some of the things that we start to see in differences of the athletic hearts. And again, maybe not so athletic hearts in comparison. All right? So so we can build up the muscle that's there. That can have a nice strong contraction to get a lot of this out. Well, what if I started to draw this muscle? Let's say I am just so muscular, I am awesome. And now I have made all of this muscle here, all right, What do you think of this heart?
Not so good.
Not so good. Why is it not so good?
Can't get blood in there.
Okay, so there's less blood.
There's less room for
Less room.
Still more energy because there's more muscles.
Okay, so interesting aspect here, isn't it? And that we've reduced this room, this ventricle, this house for all the blood with all this extra musculature. So the point being is that there's a nice balance between aspects of athletic hearts. For individuals that, for example, do a lot of weightlifting and just focus in on the weightlifting aspect, this is actually one of the risks that occurs with the heart. And that there can be so much of this extra muscle that's built there, but the downside is this, a smaller chamber for the blood that's there. Sometimes it's not necessarily a healthy heart. So again, nice balance between the aerobic and again the more muscle building there can actually help with building the strength, but have the balance and not too much. It's kind of interesting aspects as we think about what goes on with that component. One thing that we see with some really enlarged hearts, especially those of, let's say, older individuals, those that may have had a heart attack and so on, their hearts are huge, all right? And that, you know, the size of your fist is expected to be like the size of your heart. We're talking about like 2 to 3 times that size that's there. And it's a really interesting example. It's a big heart, but it's a flabby heart. So again, this would be a much bigger structure, but the muscle that's there is super stretched out. So here now you've got this big chamber and very thin muscle, and the contractions that occur there, very weak. So not enough of the blood is going to be circulating throughout in that case. So just to kind of illustrate that with this, and you see this maybe when you're looking through the skeletal muscle slides, this is no different than what you see with the heart muscle. It's something like this. And that when we think of heart muscle and come back to our sarcomeres, this is almost like the Goldilocks tale, in that, you know, the porridge is too cold, the porridge is too hot, oh, this middle one's just right. But when we think of our sarcomeres, and we've done this crazy contraction thing, with any of your muscles, whether it's skeletal or with the cardiac, there's kind of just right in terms of the resting that's there. And that if you go like this point, you might be able to have a lot more cross bridges that form. You can make a nice, good contraction. If you're stretched out a little bit more, that's there. You may only have just a few cross